Welcome to Machine Learning at Home. Today will be an unusual lesson because I will try to explain you how to make your own neural network manually. Not exactly the full-featured neural network, just one neuron called Perceptron. But that neuron can do quite a lot of stuff. It can, for example, tell one species of iris from another species. Let us start. First of all, we want to simplify our embedded iris data even more. So I will call the new data set iris2 and we'll make only 3 columns of initial iris data. So it will take iris data, we skip rows and then select column number 1, number 3 and of course number 5 because we need to have species somewhere. Okay, now next step I will convert the new species column, which is now column number 3, iris2, species column number 3, into some binary 0, 1 appearance. So like ones will be setosa and zeros will be not setosa. So I will take Virginica and versicolor together. Well, actually close enough. So iris2 third column. I will compare it with a substring setosa and answer will be true or false, but I want 0 or 1. So I will take as numeric from it. As numeric of that thing will be either 0 or 1. Okay, and now to double check if everything works well, I need to run str iris2. Alright, so we have the same number of observations, 150, but only 3 variables. 2 of them taken from the initial data set, and the third one is converted from a species in such a way that 1 corresponds with setosa and 0 corresponds with 2 other species. Now I want to have a training and testing subsets. So I will do it in my usual short way. In that way, non-setosa species will be a bit overrepresented, but it should be okay today. So iris2 dot train will be iris2, and then to select each 5th row I will make that shortcut 1 to 5 more than 4, which will make 4 falses and 1 true, and then due to rotation recycling that will select each 5th row. And reverse operation is achieved simply with exclamation mark, and of course data name should be different. So we have now 2 subsets. Now we go to next step. So we have simplification, we have training and testing, and the third step is a bit technical. I just want to simplify names. I will work with iris train subset now, and I will name 2 parts with different names. So remember we used the formula approach previously. Today we'll not, but we need to separate species information from 2 morphometrical observations. So I will call our morphometrical part XX, and that will be iris2 train columns 1 and 2. And our species part I will call YY. So YY is simply iris2 train variable number 3. Okay, I think it's obvious what are within each of them. So now we're going to next step number 4 and create 3 numbers. We can create random numbers, but I will create 3 same numbers, 1, 1, 1, and put them into variable ww. So ww will be 1, 1, 1. So what are these numbers? They are coefficients or weights. So these numbers will make our model. With these numbers, we'll make a prediction of species. So we apply these numbers to initial observations in such a way that result will be prediction of the species. Interesting. Looks like magic, but we're going to do it. So next step would be to show you how these numbers should work. So first of all, we will work with the first row of our morphometric part of training subset. So we start with row number 1. This is row number 1. Of course, it consists of 2 numbers. Okay. Now we need to apply these coefficients to row number 1 in accordance to some specific formula. That formula is a very typical linear regression formula. So we apply it in such a way that first value will be multiplied by coefficient number 1. Then we add to here second value of the row multiplied with coefficient number 2. And then we add here third coefficient without any multiplication. And result we will write in z variable. So z variable will be containing some kind of number. What is it? Well, some random bit number 7.4. Now we need kind of rule which will convert number from that formula into prediction. That is process which called activation. So we have a very simple activation. If z more than 0, then it will predict 1. If z is 0 or less than 0, negative, it will predict 0. Remember, 1 is setosa, 0 is non-setosa. This is our rule today. So we invent new variable pp, which will be result of that prediction, or in terms of neural network, activation. So I want numerical variant of z more than 0. Of course, answer will be, you can guess, since 7.4 is more than 0, answer will be true, and we convert it to number, so that will be 1. So pp should contain 1 now. Yes, it is. So now it's already step number 7. So we need to provide some way of updating our coefficient. Simply like if our prediction is correct, which is by the way true today, right now, then we do not need to update our ww, our coefficients. If our prediction is incorrect, we need some way to update them. So we will write it down, even if it doesn't update right now, we'll use that later. So let us do it and invent new variable. I call it dd. So this is the differences between old coefficients and future updated coefficients. So dd is calculated like yy, which is our species. So first value of yy, this should be 1. Remember, It is right here, we're still visible. So y11 will be 1, 2 will be 1, and then y11 will be 0 because it will be started non-cytosis species. Okay, so we'll make a difference between our actual species value yy and our prediction, which is pp. So this is a very important part. If prediction and a species are the same, then dd will be 0 and will not work at all. If prediction and species are different, then dd will be some number, and that number will be useful in the future. So, and we'll multiply it to some vector numerical set of numbers, which will consist of first value in the first row, xx11, second value in the first row, xx12, and just number 1. So this is our result. Since yy number 1 and pp are the same, dd will be 0 today, right now. Let us double check it. Yes, 3 zeros, because second part is 3 numbers, so we multiply each of them to 0. Answer is 3 zeros. And next, again, is useless right now, but will be useful in the future. We update our coefficients with dd. So simply make previous value and we'll add dd to it. Of course, our coefficients didn't change right now because they predicted well. Of course, their prediction is kind of, well, extremely superficial. We didn't mean anything when we invented these 3 ones, but it works. So it will work for some time and then stop to work because they will start to have non-cytosis species. So now we move to the second row, to the third row, to the fourth row, to the fifth row, to the sixth row, to the seventh, eighth, ninth, 10th, and finally we go to row number 11. Let me show you how it will work with row number 11. So let us go and again make ZZ, but now with row number 11, XX11 1 and XX11 2. Coefficients are just the same because they didn't change in the first part of our calculations. Okay. Now ZZ is different. And we need to make a prediction. PP, which is as numeric if ZZ is more than 0. Okay. So PP will be 1 again. Everything is fine so far. But then, this is interesting. So YY11 species now from 11 row is 0. It's not cytosa. So YY11 minus PP will be minus 1. And then for the first time, result of that calculation, DD, will be not 0 but something else. So let us calculate it first. So DD, I simply typing arrow up on my keyboard to repeat everything from my previous calculation, but don't forget to change XX1 to XX11 and YY1 to YY11. Okay. So now DD is different. It's minus 6.5, minus 4.6, and minus 1.0. And now we're going to update our coefficients. So far, our coefficients were 1, 1, 1. Now, after update, they will change the first time. So we update them. And now they are minus 5.5, minus 3.6, and exactly 0. So our coefficients changed the first time, start to be different. Then with each wrong prediction, our coefficients will change again. If prediction is right, coefficients will stay the same, and so on and so far. So we have 30 rows in our training subset, and 30 times this process will repeat it until coefficients will be changed somehow. So the system will teach itself to recognize species properly. So that's exactly the process of training our perceptron, our model. Of course, to repeat this like 30 times is extremely boring. So we need to have some programmatic advancement, some stuff which will do this thing automatically. And that we will take in my second part of Perceptron lesson. Thank you.